What's good, everybody? I'm back. Just check something out real quick. Yeah. 1 second. Freaking ghetto ass neighbors just moved in. Oh my goodness, dude. Look at that. I'm just listening to this real quick. I'm trying to figure out the music volume levels, right, guys? So, bear with me. Come here, go to advanced. Pick this up here. And let's do this. Let's move this up to. Let's go to 38 maybe. Let me just give that a second. Test, test, test. 1, 2, 3. If you're out there in the mighty world, just give me some thumbs up or something like that in the chat. Tell me if everything sounds good. Yeah, 38 sounds good. You know what? Let me bring that down actually a little bit. That is a little bit loud. Let me drop this down to 42. 42. Alright, somebody just give me some thumbs up in the chat. If that music's too loud, just give me a heads up. You can tell me to turn it down a little bit. Yeah, I like 42 decibels, a little bit better. It's a little bit better. Alright. Can you still hear it? Yeah, you can just hear it. I like that. Okay. Everything's a work in progress, guys. Alright, welcome back, everybody. We're gonna continue on. Just had to take a quick break. Thank you for everybody for joining back. Make sure you guys like, share, subscribe. Make sure you guys, wow. And I dropped everything now. What's good? What am I breaking over here? Did that screen drop down or is that just me? Let's see. Oh. Is that me that's doing that? What am I breaking? Seriously. I break shit all the time. Oh, you're taking your CCNA in a month. That's what's up. Any advice? Study and lab. Oh, hold up. Sound like my freaking washing machine was just gonna explode. Best advice for you. Yeah, lab. Study. Hey, what y'all configuring? We've gotten yeah, we can run through the configurations and stuff like that. Just make sure my screen doesn't do that little mess up again. Anything, if the music or anything like that's too loud, guys, just give me a heads up, and I will fix that. All right, so let's get into this. All right, so we're over here at CML. Tyler. What are you? So you're studying for your CCNA right now. Are you doing anything? Are you labbing with anything or anything like that? Using Cisco Packet Tracer. Um, it's the best way to do it. So yeah, so we're over here, Cisco Model Lab. Move my big head out of the way. Boom, we got Cisco Model Lab right there. If you're not familiar with Cisco Model Lab, this is Cisco's virtual emulator, where it emulates Cisco's devices. This is their free edition. I believe it's 2.8.1 free tier right now. With the free tier, now I was always a paid user. I was a big supporter, of this project. At least financially, it never actually did anything to help. These guys are geniuses who made this, but I just ain't got the money right now to pay the $200 license to be able to, use whatever Infinity and beyond. But this free tier, they created a free tier, and it's amazing, dude. You get up to 5 devices. 5 of these pretty much devices. You can use unlimited switches and unlimited external connections and stuff like that. But let me see. I'm using Packet Tracer lately into Mega Labs. Nice. You're probably more advanced than I. You probably know more than I. Maybe you can help me out. I did take my CCNA. I did take the test. I did fail it. I was studying for a while. If you go back in my past streams. But it's been a couple of years since because after I failed, I didn't even have a job or anything like that. But I was just doing it just to do it because I was trying to change up careers. But after I'd failed and I had some other life events, whatever, never really went back to it. Now, though, I have an opportunity to step into the career field. I'm deciding to go back in. And I remember a good bit. I just got to refresh everything. So that's what a lot of this is. And to get back to point, a lot of these configurations, we're going to be going through some basic up to some of the bigger routing concepts and whatnot. But this is just getting our feetsies wet again. So, yeah. If you guys have any comments, questions, concerns, anything like that, please feel free to ask me at any time. So, all right, we're gonna get right back into it, where we left off on our previous stream here. Let me just pull this up so we can get back here. All right, so what did we leave off with? I believe we left off with DHCP. We were getting everything. What do you recommend me take for practice exams? Honestly, the best practice exam is the Pearson's practice exam test platform. In my opinion, I mean, you can tailor it 1,000 different ways and all kinds of other stuff. I used to have access to it. I was using one of the biggest things, guys. If you're out there and if you are listening, O'Reilly Media. O'Reilly Media. If you do go over there and get yourself a subscription over there, you have access to pretty much all and every technical book that was ever created and published and whatnot. And then there's you have access to all kinds of online courses. I mean, it's for free. The Pearson, forget what you'll have to specify which one you're talking about. But yeah, the O'Reilly Media subscription was one of the best investments I did, but it was expensive. It was like $50 a month. And again, once I had failed and everything else, kind of went away in my life, took a back burner. But we're getting back into things. But yeah, in my opinion, that's my opinion. That was the one I used, was the Pearson practice test for the CCNA 200-301. I believe there's an update to it now with some AI stuff. I think that it's at 0.1 now. I think there's some AI incorporated into that. I do have the books. I do have the official Cisco books, but I believe they did do an update. Weldon Odom. Weldon Odom was one of the old OG CCNA trainers. He goes way back. He actually was he's the one who wrote the book on it. Yeah. All right. All right. So let's just do a couple of show commands so I can remember what the hell I had left off at. I believe again it was just DHCP. We had just got everything configured, and our pools and our hosts and all that were configuring right, if I'm not mistaken. Last where we left off. So yes, so we got VLAN 10. Yep, we still got the lease. Yep, okay. So that's where I think we kind of left off here. I'm just taking a look back at hosts. Yeah. All right, so that's where we left off. And I think the next step we were going to take was to implement DNS in this topology here using our router R1 as our DNS server. So let's get into that, and that's what we were listening to. And again today, all links are in the description on YouTube for people's content, like David Bombal. David Bumble's one of those OG CCNA teacher instructors there from way back in the day. Always a great source. The guy, still to this day, he's making YouTube videos, just blasting them out. I mean, he's an amazing wealth of knowledge, that man. And you also, some of the material that we'll be listening to and going over some of the stuff that Neil Anderson, too, another one of those real intelligent guys that goes way back. He does a lot of stuff with Python and stuff like that. Real smart guy. I've actually taken courses with him, again, over on O'Reilly Media. I've also taken courses directly with Weldon Odom, the OG guy who wrote the CCNA 200-01 book there. Again, O'Reilly Media. Can't speak enough about it. Always wish I got a freaking whatever to, like some people do with fucking social media people. Help them out. Pay me for promoting them. Whatever. Alright. So yeah. I'm gonna get back where we left off here.
First up, IP domain lookup to enable it to use DNS. Oh, and I forgot to go to global configuration. So config T first to get to global configuration, and then IP domain dash lookup should work. Next up.
Oh, I gotta remember, where's our paste bin at here? Alright, so I am creating, I do have to update some of this paste bin stuff here, but I am trying to create a paste bin. So that was so I did the DNS one. Did I finish the switch one here? Yes. Okay, so we have encapsulation trunk mode. Yep. There are some other commands, some other more specific ones to this, but that was that one. All right. And if anybody, I guess if the interest is there, I used to create GitHub pages to keep these labs on, because in CML you can download the entire lab, so you guys can look at the configurations on all the nodes inside of the lab. And I can also add pastements to that too with commands as well, if y'all are interested. Again, remember guys, like, share, and subscribe. And if you find me helpful, if you find that my content is, useful to watch, I guess, at all, or, you know, do me a favor, guys, help a brother out, buy me a coffee. Your boy can use as much help as possible. But I'm not begging here. I just need some help. So, all right. So, I'm gonna keep this paste bin up here. I'm just gonna kind of make it a little bit smaller over here. I don't need it that big. Put it there for now. It's fine. And we're gonna go back here, so you guys can see.
Is IP name server.
Configuration pool for the clients and using the router as their DNS. Yes, yeah. So, you are 100% correct. I'm using the router. So, I'll go back to the topology just real quick so you can see what I'm saying here. All right, so yes, so the R1 here is acting as the DHCP server for each VLAN here. So this switch, each interface is broken off into a different VLAN, VLAN 10, 20, 30. Each VLAN has their respective network. VLAN 1, this is network 192.168.10, 192.168.20, 192.68.30. Which you could see in the respective pools here, DHCP pools here. And we have a virtual interface for each VLAN on our Ethernet 0-0 interface here. So, and then, yeah, so now we're going to configure DNS on R1 here. And then we'll assign a name list for DNS for each one of these hosts and the switch. So then we can, send some DNS messages, and then we'll pull that up. We'll take a look in packet tracer, just take a look at the DNS messages and whatnot. So cool. All right. So get that there.
To configure where the DNS server is going to be, it's going to be itself, which is at 10.10.20.1. Then I'll configure the domain name, so IP domain. It's going to be itself, which is at 10 server first, which was R3. I'll do a show IP interface brief just to check the IP address is right on there. Yeah, 10.10.20.1. That's going to be our DNS server. So the commands I'll enter, first up, IP domain lookup to enable it to use DNS. Oh, and I forgot to go to global configuration. So config T first to get to global configuration, and then IP domain -lookup should work. Next up is IP name server. To configure where the DNS server is going to be, it's going to be itself, which is at 10.10.20.1. Then I'll configure the domain name, so IP domain -name, and for this lab I'll use Flackbox.lab. Obviously this is a different lab than the one I showed you with Windows because I'm doing it on my Cisco router now. And then the command to make this the DNS server is IP DNS server. So that's my basic DNS commands. Next up I need to enter addresses for the hosts that I want to resolve. So the command for that is IP host. The first one is R1, which is at 10.10.10.1. Then next will be R2.
So, what do we got here for information that's on this router right now? That's what I was trying to run while that was going with some show commands. So, what do we got? Let's see, DNS view default parameters, DNS resolver settings, lookup is enabled. We don't have a domain name. We don't have any search list. There is a identified as a name server, domain name server, and I believe I set that when I was starting to get into the lab. Yeah. So all right. So what are we gonna do now? We need a domain name. We don't need a search list right now. So let's go ahead and jump Drop right into the global configuration mode. So we're gonna do because we already got that. So we're gonna do just pull out auto paste quick. So our little domain name will just simply be, we'll just identify ourselves as r1.lab. All right, so we got that. And we're going to identify ourselves as the IP DNS server, and I believe that's how you initiify, pretty much turn yourself into the DNS server in the router. So I believe that's the command, is the IP DNS server in global configuration mode. So exit to, oh, that actually did something. All right, so what do we got? So let's create, we'll create some records, some host records here, and that's what he's going to go over.
I'll use command history for this, so I'll hit the up arrow to get that previous command back. I'll use 10.10.host that I want to resolve. So the command for that is address. So that's my basic DNS commands. Next up, I need to enter addresses for the host that I want to resolve. So the command for that is IP host. The first one is R1, which is at 10.10.10.1. Then next will be R2. I'll use command history for this, so I'll hit the up arrow to get that previous command back, and I'm going to edit this using the cursor keys to make it IP host R2 is it.
Alright, so I'll do a host. So IP host DNS and IP host. Yep, okay. We got host list, host routing, host names. We're just gonna do host. And okay. So we'll do host one. So host one. And that is at 192.168.10.11. So let's do this. Let's jump out of this and let's see if we can ping. So we're gonna say ping host one. And okay, so we've successfully ping host one using the host name that we used in our DNS configuration. So let's go back to do show DNS. Let's do view again. Looks like we got a lot of information on that. Okay, so what we got? Look up default domain name, default search list, domain name server. That's our domain name server right there. And let's go to show some view list. Nothing. funny that it's not showing any information on that. Wonder if there's a better show command or something. What else we got? So I wonder if it's because we did the core on this. Okay, so let's go back to configuration mode. What did we just last run? All right, so let's create a host name for us. We're gonna call ourselves R1, and again we're at 192.168 dot 1.1. Okay, and we'll do the other host too. Let's do 20.11, and this is host 2. Did I do the space in between? It's probably did like that, yeah. Right, so that's host 2. Let's create host 3. All right, so let's get out of that real quick. Let's just write this configuration real quick, guys. Let's save it. Let's ping host 3. Cool. All right, let's go over to one of these hosts now, and let's try to ping R1. Oh, look at that. So it did take a minute, but we were able to successfully resolve R1 to our DNS server. We'll take a look at those packets next too. But I do want to run some show commands now. So do show IP DNS. I don't know why name list isn't populating anything. Strange to me. Again, what is server information we get off of that? It's just telling us that, oh, so that's our server. Okay. And let's do statistics now. Okay, so we got 8 queries received and 8 queries responded to. And that, you know, is reflected in some of the packets we transmitted here. There was probably some drop packets right there, but that goes to that. And I want to find, okay. I need that. Show me. Names and addresses. Alright, I'm gonna get some more information. let's do. In the meantime, let's do this though. Show host. So ChatGPT is broken today. I don't know how I broke ChatGPT today. Show host with the most. Host with the most. All right, so there we go. So a show host. To monitor DNS activity on your Cisco router acting as a DNS server, you can use the show host command. This command provides information about the default domain name server and its cache list of host names and their corresponding IP addresses. So to view the DNS cache, enter the following: show hosts, domain names, lookup, clear. So we can clear the cache. So clear the cache, clear hosts, to clear all specific host name, to clear all, clear cache, clear all cache, additional IP. Okay. All right. What do we got? No, that's not what I wanted. I wanted this. Okay. Oh, okay. Alright, so I just want to see if there's any follow-up commands for that too. So we got it's just the same. Okay, for now. Alright. Default domain name. Yada. Oh, and if you could tell, this is written backward. Well, the IP addresses here are written backwards. If you're curious what this numbers are, it's written from right to left instead of left to right. So we got 192.168.10.11. That was host 1. It's pretty much receiving host 1's message. Well, it's got them all in here actually, where they're all at. It's just written backwards. Okay. All right, that looks good. So we want to capture some packets next. That's what we want to do. So we can see that in action. So we're gonna come over here. Yeah, we're gonna come over here. Capture, yep. Then we'll ping host 1. Okay. So let's start capturing some packets. Come over here to host 3. We're gonna say ping host 1. It's gonna take a second because it's first time resolving some of this stuff. And now we got capture all 50. I got yeah, I'm pretty sure I got it all. Let's download that. Open up where's my there. Alright, let's go back to let's open up Wireshark here. And what's gonna open that up? Thank you very much. Alright, so we're opening up Wireshark. If you guys ain't familiar with Wireshark, one of the other important things to get familiar with. And okay, here we go. So we have our DNS PDUs right here. Yeah, if you can wrap that up. Here's your headphones too. If you could turn that off too. I was just trying to. Yeah, I was listening.
That's so cool.
All right. I was I was getting the music volume, and the way that I was doing with the laptop, it just wasn't giving me the right actual volume to what it's actually playing on YouTube. So I just had to listen to the live stream real quick just to get the music volume just right. So got some chatters, chatters. What you need?
Set to clean up the kitchen a little bit, and go take a quiet hot shower.
Yeah, close that fucking window so you don't hear those fucking people yelling.
It started getting excessive music too.
Fucking wild.
Right, children.
Fucking wild behavior. Uncivilized fucking behavior. Sorry.
I need to get
Alright. Let's go back to things here. So we have our DNS request. And again, we could see some identifying information here that we have. So we have our IP address coming from host 3. And if you are curious, we can confirm host 3's IP address here. So we'll do ifconfig. So we did an ifconfig, and as you can clearly see, our IP address is 192.168.30.11. So we did a confirmation on that. Okay, go back, open this up. So from host 3, 192.168.11, it is sending a DNS request to what it knows from getting it from DHCP to 192.168.1.1. And we'll take a look at that here. The query. Let's take a look at the query. Alright, so the query pretty much asking for host 1. Let's type a name, host 1. Alright, host address. It's looking for some information. It's a AAA request. Yep, it's a AAA request. Oh, quadruple A request. Mind me. Oh, is that all that's the difference between the two? Is the different flag. Yeah. It's adding like a yeah, I'm good. Yeah, it's adding some kind of a warning flag here, warning protocol flag here, and it's DNS response missing, security level, severity level warning group. So it's adding another flag to that. And here is our response. Here is our response back. So we have our domain name system response. There's some flags right there. We don't need to worry about that. But here's our query. So host 1, type A, yada yada yada. Where is it giving me? So there's the answer. That's what I was looking for. The answer. So here's my answer right here. We already know our query. We need the answer. And inside of this PDU, R1 is supplying us with our DNS answer, host 1, yada yada, address. So here's it giving us our address right here, 192.168.10.1, host 1, yep, time to live, and it's the address again. So cool, that is pretty cool to take a look at. And so again, this is just query just from coming from host 3, and we're looking for an answer coming from our DNS, and we just took a look at our answer here, supplying us with all the pertinent information that we need. And see, so okay, so here comes some of our replies back. So okay, so back, yeah. this is coming from. I broke everything for a second. I don't know what happened for a second. I was afraid. I was getting scared. What do we got? What do we got? What do we got? There's some art messages. Okay, where are these art messages coming from though? Some source. Sender. Oh, so this is okay, so DNS and then then it's sending its art messages because now it needs to know like how to route it there, right? That's what it's asking for. Who has it's the host asking for its router. It's looking for its router. That's what it's looking for. That's what I'm saying. Yeah, okay. So yeah, sender IP address, that's host 3, and it's looking for its router. That's where its router obviously it's R1, that's one of its virtual interfaces, and we can go and we can take a look at that just so you guys can see what I'm saying. So show IP int brief. Yes. And here is its virtual interface right here. So 192.168.30. And inside of DHCP, so AP DHCP pool, and it's not giving me. I wanted like a better summary of that. Yeah, that's fine. All right. Let's go back to. We got that. Yeah. So yep. So it's looking for that. Sending its art messages. And what are we getting back? Sender. Target Mac. Target. Yep. When did this? But where are you sending this one? Where did this go? I think this. Oh, this might have been one of like the flood. Yeah, when it was trying to flood it out of the switch port, I believe. All right. Oh yeah, that takes a look at that. So cool. All right. So what do we got now? Let me just save this configuration. See what we got going on. We currently let's do a show run. Just want to see the whole entire configuration we got going on here. This stopped, right? Yeah, this stopped. Get that out of there. I want to make sure that's not still trying to collect packets, even though it says it's not. Never tell. This thing to run away on me. Let me go back to this. Boom, so you guys can see a little bit better. Alright, so we're just looking at the configuration we got so far. So here's our excluding list, DHCP exclude address list. to our GCP pools. So here's some of our host name list, yada yada. Yep. Okay. Some of our interface information here. All right, so we've covered DHCP, we've covered DNS. All right. Just go to host 2, just make sure host 2 ping, we'll say R1 this time. Oh, okay. Cool. So we pretty much have a pretty basic but functioning network, where we've got host names being resolved, dynamic addressing, come over to the switch. I've taken a look at the switch in a while. Let's do, what are we doing for show commands here? What are we doing with the switch here? Let's do a show interface VLAN brief, maybe. We got all that squared away. I wonder why it doesn't show, and I think I heard that before. It doesn't show when you have something. It's because is it truncated? Is that the reason why it's not showing up there? Why is zero, which is the port switch? For routing. Show up on. Okay, I'm just gonna ask that question. Let's get an answer real quick. So pretty much what the question was is, why isn't the trunk port showing up on the VLAN brief when we do the show VLAN brief? I believe I remember the trunk ports don't show up for some reason like that. I'm on. I swear I broke ChatGPT. I broke it. Okay, so all right. So in Cisco switches, the show VLAN brief command displays VLANs in their associated access ports. However, trunk port interfaces configured to carry traffic for multiple VLANs do not appear in this output. This is because trunk ports not assigned to a single VLAN. Instead, they are configured to carry traffic for multiple VLANs. Therefore, they are not listed under any specific VLAN in the show VLAN brief output. So to see that, yep, this command, so the show interface trunk. So we'll run that. Show in trunk. Alright, so we show in trunk. So what do we got? So we got our Ethernet 0-0, mode on, encapsulation method, status trunking, native VLAN 1. VLANs allowed to trunk, so we have 1, 10, 20, 30. VLANs active. VLANs in the spanning tree or forwarding state and not pruned. So I think maybe we spend some time and do some stuff with switches, maybe, because for the most part, I think for the most part when it comes to routers right now, I think the next logical step of routers is the routing protocols, bigger routing protocols, OSPF, ERGRP, what is it, BRB, there's a couple of them, but those will be the next logical things we start stepping in. We start going over with routers and configuring those. Maybe we spend some time doing some switch stuff next. Yeah, because we can maybe mess around with ignoring certain VLANs, not allowing certain traffic to flow between VLANs and stuff like that. Maybe we took a dive into that, because we got spanning tree, got root bridge stuff too. That's all the nitty gritty of switches, but yeah. What's this? Let's do this. Let's go back to
10.10.10.2. Then the up arrow again. The next host is R3, and that is at 10.10.20.1. So that's how you do your host. I'll also enter these as FQDNs as well to show you how to do that. So IP host R1.flackbox.lab is at 10.10.10.1, and then R2 is at 10.10.10.2. So I just use the up arrow again there, and I'll edit this and make that R2.flackbox.lab in the correct IP address. And then the last one, IP host R3.flackbox.lab is at 10.10.20.1. So that's all the config that I need for my DNS server. Next up, let's configure R1 to be a DNS client. So I'll go in here, I'll go to global configuration, and then IP domain -lookup.
see what it did. Let's clean this up. Let's clean this up a little bit. All right. Go back to the router. Let's clean this up a little bit. Oh, they're doing like a major update on ChatGPT or what, man? So slow today. I'm not even asking for it to create pictures, just the text is so slow. Create a small model on my freaking Raspberry Pi that runs fast on this right now for some reason. was actually going to be one of my projects that I was actually going to be working on. I was thinking about streaming is deploying a small model LLM on a Raspberry Pi and do some stuff with it. So all right. So name of priority. All right. So I'm going to clean up this on how I did some of the naming convention on my default domain name. So I believed, yeah, it's just not, the naming convention is just not right. Even it did. Yeah. Default domain name, I don't like that, so let's fix that. Alright, so we're gonna say IP domain name. And we're gonna say our domain is lab.com. Okay, so we changed that. Now let's go back into the configuration mode, and I want to do some better butters. So we're gonna do IP host. Yeah, we're gonna do this a little bit better. So one. How did I? Oh, let's do a do show. IP host. Are they screaming help? I can't take this. These fucking people aren't. Don't smoke fucking meth, kids. I got headphones on. I can fucking hear them still with my headphones. I got all the windows in the house closed. Oh my god. Give me 2 seconds, guys. That's bloody fucking murder. You think I live in a fucking trailer park? White trash, I'm just not that white of trash. Alright, so let's go back, guys. So, IP. What are we doing there? What are we doing there? IP host r1.lab.com. That's that one, that too. Say something. And 1.1. That's 11. It's gonna be 10. It's gonna be host 1. Looks good. Yep. Host 2. And finally, host 3. Okay. All right.
To allow it to use a DNS server, then IP name dash server to configure where the DNS server is. That's on R3, which is at 10.10.20.1, and then the DNS suffix, I'll say IP domain dash list flackbox.lab. Now if I'll use end to drop back down to the enable prompt, and let's see if I can resolve hostnames now on R1. So I will try pinging R3 by its hostname, and I can see it's resolving it at the domain server at 10.10.20.1. It then resolved that, and I can see that the success rate was 5 out of 5. So that looks all good. Let's also try pinging R2. So this will also be resolved by the DNS server at 10.10.20.1, and it resolved that to 10.10.10.2, and I was able to ping that too. So that's how you configure DNS on your Cisco routers. Next up, we'll have a look at ARP in the next lecture.
I'm gonna go over ARP for a little bit. Do that.
In this lecture, you'll learn about ARP, the Address Resolution Protocol. As usual, we'll start off by looking at how this fits into the OSI stack. So we've got a sender on the left that's going to send some traffic to the receiver on the right. The sender will compose the packet, starting off with the layer 7 information, that's the application layer. It will then encapsulate that with layer 6, the presentation layer header. That will be encapsulated in the session layer header. Then at layer 4 with the transport layer header, which will include information such as whether it's TCP or UDP and the port number. That will then get encapsulated with the layer 3 IP header, which includes the source and destination IP address. That will then be encapsulated in the layer 2 data link header, which includes the source and destination MAC address, and that will then get put onto the physical wire. So as you saw in the last lecture, the sender can either send directly to an IP address or it can send to an FQDN. If it sends to that fully qualified domain name, then that will need to be resolved into the IP address using DNS. So we'll find the destination IP address, then when the packet gets down to layer 2,
so I want to know I don't know what all this means. Let's do a copy of all this real quick. Just want a clarification on when it's, you know, some of the clarification on, you know, class type, TDL, all that stuff, just to clarify a little bit of my more understanding of what I'm looking at here. All right, so let's break it down, including both. So the command lists both forwarding A and reserve, reverse PTR lookup entries. So PTR. So PTR, look up what PTR means, but it's saying that these are like reverse entries. As ChatGPT explodes. ChatGPT is hurting today. All right, understanding the fields. This is either domain name for a record or reverse map IP address in the in-adr.arpa format for PTR records. TTL, time to live, indicates how long in seconds the DNF entries remained valid in the cache before it needs to be refreshed. In this output, all entries have a TDL of 10 seconds. Class specifies the protocol family. The IN stands for Internet. So the IN stands for Internet, which is the most commonly used class type. So what we got? An address record that maps a domain name to its corresponding IP address. PTR, point, a pointer record used for reverse DNS lookups, mapping an IP address or corresponds with a domain name. Forward and reverse DNS entries. A record forward lookup. These entries map host names to IP address, for example. A PTR record reverse lookup. These entries map IP address to host names. Represent reverse order. This indicates the presence of both A and PTR records ensure that both forward and reverse DNS lookups can be performed successfully. Alright. Say with the A records, yeah. A forward lookup. In that. Everything looks good there. I'm pretty satisfied with that because I can come over here. Go to host 2 now. I'm gonna say ping host 1 lab.com. Alright, and we successfully resolved it. Cool. Cool. Alright. So, I think that pretty much covers that then. Would you satisfied?
The sender needs to also know the destination and MAC address. So when it composes a packet, it needs to know both the destination IP address and MAC address as well. Now, the IP address is a logical address which is controlled by administrators, so it makes sense that we can have that referenced in the application, either directly as the destination IP address or as the FQDN, which can be resolved by DNS. But the MAC address, on the other hand, is not a logical address. We just have that great big flat global address space. So it's not really possible either for the user to enter the destination MAC address himself or for it to be configured in the application. So because of that, we need a way that it can be automatically derived. We need a protocol that's going to be able to figure out what the MAC address is automatically. And that's what ARP is, the Address Resolution Protocol. ARP maps the destination IP address to the destination MAC address. So in the example here, we've got a sender on the left at 172.23.4.1, and its MAC address is 1.2.3. And it's going to send some traffic to the receiver on the right with IP address 172.23.4.2 and the MAC address 2.3.4. And in our example, the sender already knows that it wants to send traffic to IP address 172.23.4.2, so it can compose the packet as far as the layer 3 IP header, but it doesn't know the receiver's MAC address yet. So it's going to use ARP to find that out. So it will send out an ARP request, which is a layer 2 broadcast. The ARP request says, hey, I'm looking for 172.23.4.2.
Just to... We did take a look at that right here too, just to show everybody, you know, I guess just to go over it. We have our protocol here, our address resolution here, the sender's MAC, the sender's IP, and it was looking for the router's MAC and IP. Yeah, it didn't know. Oh, okay. So yeah, so you can see right here. I'll highlight this right here. So we have our sender MAC and IP address 192.168.30.1, which is host 3 right here, and it is ARPing this message out because you can see right here it does not know the MAC address for its target IP, which is 192.168.30.1, which is the virtual router interface on the router there. Let's take, and then this was the response back. Yep. Yeah. Okay. And this was the response back with the MAC address information for the for 192.168.30.1. So now it gave it its MAC address information. Instead of that be filling with zeros, now it has populated with its info, and that's its reply. Cool. So ARP is a protocol in which a host sends out a message with an IP address saying what MAC address belongs to this, you know, what host with this IP address, what's your MAC address? Pretty much that's what ARP is pretty much doing.
What's your MAC address? That will come from the sender's MAC address of 1.2.3, and it goes to a destination MAC address of f.f.f. That is the layer 2 broadcast address. Obviously, the sender has to send it out everywhere because it doesn't know what the intended destination's MAC address is yet. That will come into the switch. The switch will see that it is broadcast traffic, so it will flood it out all ports. It will hit everything plugged into that switch, including, in our example, the receiver on the right, which will process that ARP request. It will see that it's looking for 172.23.4.2, and that is its own IP address, so it will respond to the ARP request. It will send an ARP reply back saying, I'm 172.23.4.2, and here's my MAC address. That comes from its source MAC of 2.3.4, and the destination MAC address is the original sender's unicast MAC address of 1.2.3. The receiver knows exactly where it's to send it back to because that original MAC address of 1.2.3 was in the ARP request. The switch will then send that ARP reply just out of port 1 down to the original sender because that was unicast traffic and it's for a known MAC address which is already in its MAC address table. Okay, so that is how ARP works when both of the hosts are on the same IP subnet. ARP replies are saved in a host ARP cache so that it doesn't need to send an ARP request every time it wants to communicate with somebody else. To view the ARP cache, we can do that on Windows with the ARP-A command. On a Linux host, we use the ARP-N command. You can also see the commands there on the slide to flush the cache if you need to. We wouldn't normally do that, but if we were troubleshooting it, or if the ARP cache had somehow got corrupted, that's how we would clear it. So let's have a quick look at that in the lab. So I'm here on a Windows host.
So we have that right here. So we're on host 3 right now, and I just pulled up its ARP cache by doing the command he did, ARP -n. Obviously I did try ARP -a first, but ARP -n, and we get our only cache right here, which is the router, and we have its MAC address right here. So let's try this though, see if we can populate something else. Ping, we'll say host 1. Wonder if capitalization and stuff like that matters. Well, we're gonna find out, I guess. Let's see if this resolves. Yep. So it resolved back. And cancel that. Now let's see ARP -n now. I think it's not sending those ARP messages to find out where, because it's obviously it's on a different network. Where the router, the virtual interface is on the same, at least for the most part, resides on the same logical network as that one is. So that could be it. I just wanted to take a look at that just to shits and giggles there. So continue on.
Let's have a look at the IP address. It's 172.23.4.1. For this example, I've got a Linux host at 172.23.4.2. So let's ping that to generate some traffic.
This. Did we already look at the route tables on this? What do we got here? Yeah, so on the router has a complete ARP table with MAC addresses, corresponding IP addresses, interfaces.
Okay, so in the host here, I'm going to ping 172.23.4.2, so it knows what the destination IP address is, but it doesn't know what the matching destination MAC address is yet. So it's going to do an ARP request to find that out. That happens in the background, you don't see it happening here. In the last lecture, you learned about ARP, the Address Resolution Protocol, and how it's required to allow communication between two hosts over an Ethernet network. In the last lecture, you saw how it works when both hosts are on the same IP subnet. In this lecture, we'll cover how it works when they're on different IP subnets. So you already know
so this
that,
pretty much
that means that the traffic is going to have to go via a router. So
this is
we'll
what
work
we
through an
pretty much
example
just
for this. In the
talking
example,
about it.
172.23.4.1 wants to send a packet to 192.168.10.1. So that's two different IP subnets. So you see the sender over there on the left, the receiver is on the right, and we've got a router which is going to route traffic between those two subnets. So we can't have ARP working the way it did earlier when both hosts were on the same subnet. If the sender on the left sends out a normal ARP request for 192.168.10.1, that will go out as a layer 2 broadcast, and it wouldn't be forwarded by the router, so the ARP request would never get to the receiver. So obviously that isn't going to work. Also, we know that when we send traffic between two different IP subnets, it has to be sent via a router. So the sender is not going to send an ARP request for 192.168.10.1. It knows not to do that because it compares its own IP address and subnet mask with the destination IP address, and it can see that it's on a different IP subnet. So the sender knows that it has to send the traffic via a router, so it doesn't send an ARP request for the final destination, it sends an ARP request for its default gateway. So the sender at once...
Yeah, so from yeah, when we pinged here, so when we pinged host 1, once it gets back the DNS name resolution, and it sees that the host that we're trying to communicate with is not on the same network. It doesn't actually send out an ARP message.
172.23.4.1 will send an ARP request for 172.23.4.254, which is its default gateway. That comes from a source MAC of 1.2.3 of the sender.
Yeah, so the router would be the one that would send probably the ARP request out.
The destination MAC is, as usual, for an ARP request, f.f.f, the layer 2 broadcast address. And in the ARP request, it says it's a request for 172.23.4.254.
Yeah, I guess we go over CDP and LLDP. I think that's the Cisco Discovery Protocols.
In this lecture, you'll learn about Cisco Discovery
Protocols.
Protocol, CDP, and the Link Layer Discovery Protocol, LLDP. They're both very similar protocols. CDP, Cisco Discovery Protocol, is a Cisco proprietary Layer 2 protocol, and it's used to share information with other directly connected Cisco equipment, such as the operating system and the IP address. That information will be shared between connected devices. That aids in troubleshooting by allowing administrators to map out how Cisco devices are connected to each other. For example, say that you're in New York and there is a problem in Sydney and you don't know about the network topology in Sydney. Well, as long as you can jump onto one device there, then you could use show CDP neighbors to map out how all the other Cisco devices are connected to each other. So it's a very useful troubleshooting tool. Even if you know what the topology should look like, you can use show CDP neighbor to check that the device is there and detected at layer 2. CDP is enabled by default on most Cisco equipment, not just on routers and switches, also on the firewalls, and even things like software, like Cisco Unified Communications Manager, which is used to control IP phones, and even the IP phones as well will run CDP. So if you go onto a switch, which has got the Cisco Unified Communications Manager server and IP phones plugged in there, you'll be able to get information about those devices. CDP works at layer 2, so it's not necessary for the device to have an IP address on it for it to be detected by its neighbors. The commands for CDP, so it's enabled by default. If you want to disable it, you can do a no CDP run. To turn it back on again, it's CDP run. That's done at global configuration. A reason you would maybe want to disable CDP.
So if we run show CDP neighbor from our router here, this is something I brought up in a couple, I think the past stream or the other past stream, whatever. Even without having an IP address, none of that. As soon as you make a connection, and that interface port is on, has to be on, the Cisco's equipment's going to start sending messages out. It's going to start sending these Cisco Discovery messages out, these CDP messages, looking for other Cisco equipment, kind of mapping it out. Where is it off of its port, its interfaces and whatnot. And that's where when we first created the lab, before again I did any IP assignments or anything like that, the switch and the router were already communicating with each other, discovering some of the basic information, like the device ID, the platforms, capabilities, what it actually is. This is a layer 3 switch, so that's why I say it's router switch. The interface, the outgoing port ID, if there's a port ID, some of the software information, the MAC address, the VLAN, the duplex. If we go over to the switch, we can do the same thing. How you doing, honey? You good?
Yeah.
I'm not finished with that yet.
Oh, okay.
I'm still drinking that. It's still good. That was really good, by the way.
I put the rest in the fridge.
Did you?
I just got my water over here.
Thank you. So we come over to the switch and we do CDP neighbor as well. Well, we'll do detail. And we get something, some very similar information here. It must have just updated. So now it's given us device ID because we have DNS. I believe this is probably what we'll have to look at some of the updated CDP messages to see where it's saying that, because that must have just updated itself. So IP address, where it is, where it's connected off of the switch, its port, whatnot, its MAC address, duplex, and its management address too, right there as well. So that's CDP. So it's a discovery program for Cisco equipment to map itself out. Okay. And LLDP, I believe, is a very similar one. Just not Cisco, I believe. It's gonna touch what? Yeah, I see right here.
CDP, I'll go back to the slides for LLDP. So LLDP is the link layer discovery protocol. This came out a lot later than CDP did, and where CDP is Cisco proprietary, LLDP is an open standard. So it's supported on most vendors' devices, and it provides similar information to CDP. It does have some differences though. CDP will always be enabled by default on Cisco routers and switches, but with LLDP, it depends on the switch and version, whether it will be enabled or disabled by default. LLDP is only supported on physical interfaces. CDP is also supported on virtual sub-interfaces as well. You'll learn more about those in the VLAN section later. With LLDP, it can only discover up to one device per port. CDP is able to discover multiple devices per physical port because it does support those virtual sub-interfaces, and LLDP can discover Linux servers, CDP cannot. Our commands to configure this on a Cisco router or switch: to turn it on or off, at global configuration we've got LLDP run and no LLDP run to turn it off. So similar command that we had for CDP. To disable it at the interface level, we do it for both transmit and receive separately. So
now I think best, the best practices, I guess the word I'm looking for. Best practices is, if this is a border or edge router, not to have CDP running on any of the outgoing interfaces. Only have CDP or LLDP, if anything, running off of anything interior facing, not anything exterior facing. That way it's not actually wasting bandwidth by sending out these messages to the greater internet. There can't be discovery back, possibly somebody on the great big internet finding out information that they don't need to find out. Okay. So that's CDP and LLDP. We got that. That's just some of that. Boot up processing, upgrading, connecting static routes, default routes. Dynamic routing protocol versus static. Okay, we'll get to some of that right there.
In this lecture, you'll learn about the basics of dynamic routing protocols and how they compare to using static routes. When a routing protocol is used, routers will automatically advertise their best paths to known networks to each other. Routers will then use this information to determine their own best path to those known destinations. And if the state of the network changes, like if a link goes up or down, or if a new network is added to the topology, then the routers will automatically update each other with that information. Routers can use that information to automatically calculate a new best path and update their routing table in accordance with those network changes. So let's look at an example here. I've got 3 routers, R1, R2, and R3. To the right of R1, I've got the 10.0.1/24 and the 10.0.2/24 networks. R2 and R3 are not directly connected to those networks, so they're going to need a way to find out about them. I could either use my traditional static routing, which would require me as an administrator to configure static routes everywhere, or we can have them learn it automatically through the use of dynamic routing protocols. So what we'll do is we'll configure a routing protocol on both R1, R2, and R3, and they will then share information about their networks with each other. So we do that, we do the configuration, and R1 and R2 form a peering relationship with each other, and R2 and R3 also form an adjacency. R1 will then advertise its routes to R2. So it tells R2, hey, you can get to these networks via me, 10.0.1.0/24 and 10.0.2.0/24. That information will come in on the Fast Ethernet 0/0 interface on R2, and it will see that it came from R1 on the IP address of 10.0.1/24.
Alright guys, I'm going to take a quick 10-minute break. I gotta go to the bathroom. I'll be right back. In the meantime, enjoy some dad jokes. And I'll be right back. What's good, y'all? Alright.
And it will then use that information to update its routing table. So the routing table will now show that it's directly connected to the 10.0.0.0/24 network. That's on fast Ethernet 0/0. It's also directly connected to 10.1.0.0/24 on fast Ethernet 1/0. And the two routes that it learned about from R1, 10.0.1.0 and 10.0.2.0/24, both have the next hop of 10.0.0.1, which is on R1, and they're reachable out interface fast Ethernet 0/0. R2 also has a relationship with R3, so it will advertise information there as well. So R2 will tell R3, you can get to these networks via me, 10.0.0.0, 10.0.1.0, and 10.0.2.0, all with a /24 mask. So R2 doesn't just advertise the routes it's directly connected to, it advertises the routes that it learned from R1 as well. Again, R3 can now update its routing table. It's got routes to 10.1.1.0 and 10.1.0.0/24, which are connected on fast Ethernet 0/0 and 1/0, and the routes that it learned about are 10.0.0.0, 10.0.1.0, and 10.0.2.0/24. They're all reachable out its interface fast Ethernet 1/0, and the next hop address is R2 at 10.1.0.2. So again, just like with our static routes, R3 does not see R1 as being the next hop because it's not directly connected to it. The next hop is always going to be reachable on a directly connected interface. That's R2 in this example. So that was how our routes got propagated from right to left, from R1 to R2 and then on to R3. Obviously, the same thing is going to also happen in the opposite direction, where R3 is going to advertise its routes to R2, which will then advertise them onto R1. So with this set up, all of the routes everywhere will be advertised everywhere, and the routers will update their routing tables with that information. Just like we could with static routes, we can use summary routes with our dynamic routing protocols as well. So the same example, but here R2 is going to learn about the 10.0.1 and the 10.0.2.0/24 networks. Rather than advertising the 2/24s to R3, we can have this configured so it will send a summary route to R3. So rather than the two individual /24s, it advertises 10.0.0/16. Reasons we would do this. Summary routes lead to less memory usage in routers as their routing tables contain less routes. Obviously in our small example there it wouldn't make much difference, but this can make a big difference in really large networks. They also lead to less CPU usage as changes in the network only affect other routers in the same area. To explain this, I'll go back a slide. Let's say that the 10.0.1.1 link on R1 goes down. Well, when that happens, R2 will be notified that the link has gone down. And maybe there's an alternate path. Maybe up on the top, we've got R4, which has also got a route to get to 10.0.1.0 network. So when a link goes down, routers that have a route to it will reconverge. This means that they will recalculate.
Alright, so this is giving me... Might want to create a new lab to do this. Let's do that. Let's make sure though we save all of our configurations on our devices before we shut this lab down and create a new lab. Change the name of this one. I'm gonna call this one router on a the router on a stick lab. Alright, so all of our configurations are saved on both our devices here. Let's shut everything down. We got lab shut. Got that. Alright, let's create a new lab. be routing protocols. So we have our 5 devices. Alright, so we're going to how many interfaces these ones have? Got 4 each. That's perfect. Let's start getting these guys on. I'm gonna have to increase the disk size on this server. Okay. What should be our naming convention, guys? Let me do this actually. All right. A slab. Dynamic routing protocols. All right. Let's get some ideas real quick. pretty sure I broke it. Chat GBT did it. Oh, there it goes. Heard me talking about it. All right. So we're gonna sign a dynamic routing lab with 5 routes. Excellent way to deepen your understanding. Here's a structured approach. Naming convention, IP address, facilitates clarity, scalability in your lab setup. Naming convention. So. Interface. Loopback interface. Use a loopback interface for router for identification and routing protocols. Name them as such. IP addressing schema. Well plan IP address schema is critical for network organization scalability. Easy approach. Easy enough. Assign IP address for routing identification. Point-to-point links. Oh, that's what. Okay, and the point-to-point links. Base. LAN. Excuse me. So this is, maybe he'll go into that. Point to point. I don't know what it's.
Calculate a routing table, we'll try to find an alternate path. That takes up CPU cycles on the router. So R2 does have a route to 10.0.1.0/24, so it's going to have to do that. R3, on the other hand, just has a route to 10.0.0.0/16. It doesn't have that individual route to the 10.0.1 network, so its routing table doesn't actually change. Because it doesn't change, it doesn't need to recalculate anything. So because we were using summarization, R3 is going to be using less memory, it's got less routes, and also because we've compartmentalized our network, any outages or any changes are only going to affect that part of the network. They're not going to be propagated everywhere, which is going to take less CPU cycles on our other routers, not in that part of the network. Okay, so let's compare our dynamic routing protocols with static routes. It should be pretty obvious that dynamic routing protocols are more scalable than administrator-defined static routes. Using only static routes everywhere is really only feasible in very small environments. Reasons for this: with our dynamic routing protocols, the routers automatically advertise available subnets to each other without the administrator having to manually enter every route on every router. With static routing, the administrator does have to enter manually routes everywhere, which obviously is going to be very tedious and time consuming. Also, with our dynamic routing protocols, if a subnet is added or removed, the routers will automatically discover that and update their routing tables. Static route doesn't do that because it's all configured manually. And if the best path to a subnet goes down, dynamic routing protocol routers will automatically discover that and will calculate a new best path if one is available. With static routes, everything is manually configured by the administrator. It's a lot of admin work, and it doesn't really recover very well from any failures. That's going to require additional manual admin work again. So you're probably thinking that in real-world environments, we're going to use a dynamic routing protocol. And yes, for sure, in all but the smallest or test environments, we're always going to use a dynamic routing protocol. But that doesn't mean that we don't use static routes. It is pretty common that you'll use a combination of both a dynamic routing protocol and you'll also have some static routes there as well. In that case, the bulk of the information is going to be carried with your dynamic routing protocol. You're only going to use static routing for special use cases. For example, if you want to configure a backup route or for a static route to the internet. Now, that default static route to the internet, you're only going to need to do that on the router that is actually connected to the service provider. And all of the other routers
So, looking for suggestions too. anybody out there. I want to do something where, we'll probably have, maybe some straight through paths, but you work around too. So if something does go down, we'll see when routes change and stuff like that. So let's just take a look. See here. So pretty much create maybe a dynamic route like that. And maybe have one of them down here, connected it in that route. And so this will be another one. But how would I make it weird? So oh, I get, yeah, that's what I can do. So I can put another one right here. It's like that. So and that's where it would be the choice. Because it's an equal route like that. But if I was to take out one of these, it would then have to make a choice. How do we redesign that to make that a little bit more? I could. Yeah, you can break the chain either way. So that works. That's what I'll do. That's how I'll set it up. That way we can see when the changes are being made. So, alright. Yeah, let's set up the links now. So, link there. I will say, let's go. Add a link. Separate these a little bit. So see links. Now we'll do you right here with looks pretty good. Looks good. All right, so now we should do some of this. Let's do this. We're gonna tag it. So this would be the 10.0 dot We'll say 1, just to keep it simple. 1.0/24 network. This will be the 10.0.2.0/24 network. This is going to be the 10.0.3.0/24 net. 10.0.4.0/24. Excuse me. .5.0/. Very good. Let's get some of these opened up now. Two. And yeah, you can obviously we're already having discovery protocol messages. We'll look at CDP. You'll see CDP messages and stuff like that. Take a look at that in a second. R4. Finally, R5. Very good. All right, so we got all of our routers set up and stuff. Now we're gonna go over What should we do next? What should we do next? We're gonna yeah, we're gonna dynamically. No, we're not gonna dynamically. We're gonna statically address all of our interfaces here. Let me see. Yeah. Do show. No CDP entries. Oh, there are no CDP entries. That's right. Because I haven't turned any of these interfaces on yet. Good. So we can take a look at when all that happens and stuff like that. That's correct. So there are no CDP entries. All right, let's get started. So again, the way the convention is going to be going. This is going to be off this interface. This is going to be our one network. Oh wait, because I got multiple. I'm going to have multiple networks. That reminds me too. So I got to create a network for each one of these. So this is what I'm going to drop. So there has to be each one of these. Okay. Which is fine. It's fine. It's just going to take a little bit more thinking of things. So I'm not doing it straight through. And that way I can drop some stuff too. I guess this wouldn't really. So how would this be? Just trying to figure out how this would be realistic. Should I do it with a switch? That might be actually the way I should be doing it. Yeah, let's do it like that. So, and we're gonna do it like this. And the good thing is I can have as many of these unmet switches as I need. It's 5 of them. Okay. Got 5 switches. Let's turn these guys on. So It's all unmanned switches, so I don't get penalized for these as nodes. In the Cisco Model and Lab 2.8.1 free there. It's free, guys, so might as well use it. Alright, spread things out here, buddy. We got you. I'm gonna get you in here. Right there. That way I can see the links. Alright, so we got one link there. Very good. Very good, very good. And this will allow me to move things around too. Doing it like this is a smarter way to do it. It's true. So we're gonna need. What we'll do this. Let's do this. Let's add to each. Let's add a 10 suffix to each. So. Is that what it was going over with? There was. Let me go back to that. Hold on. It might have had a point there with the IP addressing schema. It does. Doesn't solve for. Doesn't solve for that. Let's change this addressing schema. So we'll do for its point to point. You know what? We'll keep that as its, but we'll add. Okay, that's fine. So 1.0/24. That's fine. We can maintain that. Let's change this. Add a good color. What color is red? Whatever. But we're going to add 2. Okay. Also going to add for its point to points 192.168.1.0/24, and then we're going to do 192.168.0/0/24. So what I'm going to do is I'm going to add a 10 prefix to each other side. So we're going to have 2 on each side saved and ready to go for when we need to do that. Nope, that's not how I wanted it to do that. Good dog. Okay, 192.168.1.0/24. I'm just adding these notes so I can remember myself as I go along too, guys. I don't want to forget. So we'll maintain the 10 network as like a loop back, because I'm pretty sure we're going to use that too. So unhighlight that. Just erased it. That's good. I'm gonna add that back 10, 0, 1, 0. Very good. Stop fucking around. Same thing here. 92, 168, 2, 0, slash 24. And on the other side, I'm gonna have 192, 168, 20, 0. Six eight not 3.0. So that'll give us two interfaces, and I can understand that topology a little bit better. Yeah, because I'll switch to right here. Cool, that works. Because then I'll have to do this then. Take this next one. Over here. Cool, cool. so I got. That. What I'll do is with you. That's what I'll do. Perfect. Perfect, perfect. Because then I can always, then I can always route the traffic a different way. Perfect. Perfect lab. That's a perfect lab. All right. So, there we go. This should work now with the switches, and again, these are unmanaged switches. Oof, excuse me. There's no, there's no intelligence or anything like that, or whatnot. So this should all work perfectly. All right, so we got our one right here. And you guys are aware of what our naming convention are going to be. So on our interfaces, we're going to use the 192.168 suffix to begin each network, and then from there, out of their, which side should I do it? Out of their, we'll do it like this. Out of their, each side of their 0-1 interfaces. But no, I can't do that because I'll use their, with their 0-0 interfaces, I'll use the single digit network prefix, and then on their -1 interfaces, I'll use the 10 prefix, network prefix for that, because we won't have one for the R5 right here. So let's dive into it then, as we should. Let me pull this up for you guys.
Honey, clear your throat or take a sip of water.
Mm.
If you smell gargly, it's hard to hear you.
Thank you. All right, we're back, and we're back. Put down there so you guys can see what I'm doing.
on the router. So R2 does have a route to 10.0.1.0/24, so it's going to have to do that. R3, on the other hand, just has a route to 10.0.0.0/16. It doesn't have that individual route to the 10.0.1 network, so its routing table doesn't actually change. Because it doesn't change, it doesn't need to recalculate anything. So because we were using summarization, R3 is going to be using less memory, it's got less routes, and also because we've compartmentalized our network, any outages or any changes are only going to affect that part of the network. They're not going to be propagated everywhere, which is going to take less CPU cycles on our other routers, not in that part of the network. Okay, so let's compare our dynamic routing protocols with static routes. It should be pretty obvious that dynamic routing protocols are more scalable than administrator-defined static routes. Using only static routes everywhere is really only feasible in very small environments. Reasons for this: with our dynamic routing protocols, the routers automatically advertise available subnets to each other without the administrator having to manually enter every route on every router. With static routing, the administrator does have to enter manually routes everywhere, which obviously is going to be very tedious and time consuming. Also, with our dynamic routing protocols, if a subnet is added or removed, the routers will automatically discover that and update their routing tables. Static route doesn't do that because it's all configured manually. And if the best path to a subnet goes down, dynamic routing protocol routers will automatically discover that and will calculate a new best path if one is available. With static routes, everything is manually configured by the administrator. It's a lot of admin work, and it doesn't really recover very well from any failures. So that's going to require additional manual admin work again. So you're probably thinking that in real-world environments, we're going to use a dynamic routing protocol. And yes, for sure, in all but the smallest or test environments, we're always going to use a dynamic routing protocol. But that doesn't mean that we don't use static routes. It is pretty common that you'll use a combination of both a dynamic routing protocol and you'll also have some static routes there as well. In that case, the bulk of the information is going to be carried with your dynamic routing protocol. You're only going to use static routing for special use cases. For example, if you want to configure a backup route or for a static route to the internet. Now, that default static route to the internet, you're only going to need to do that on the router that is actually connected to.
And we'll work on some of that stuff too, with doing static routes and stuff like that to see how it's going to mess up and play with OSPF and whatnot.
To the service provider. And all of the other routers inside that, what you can do is on the edge router, you can propagate that default static route into the routing protocol, and then you can have the routing protocol carry it through the rest of your network. So you're not going to need to configure a default static route on all of your routers, just the one that is on the edge. Okay, that's everything I needed to tell you in this first introductory lecture. Let's have a look at that information in the lab. We'll do that in the next lecture. In this lecture, I'll do a lab demo showing the basics of how a routing protocol works. So the lab topology, we've got those 5 routers again, R1 to R5, and I've already configured IP addresses on all of the interfaces. So first thing I'm going to do is to configure a routing protocol. Now, the focus of this section is not on the routing protocol configuration. We'll get into that when we cover each of the routing protocols individually in their own separate sections later on. The point of this section is to show you the commonalities, the things that work the same on all of the different routing protocols. So I'm going to use RIP, the routing information protocol, for this demo, and I'll show you the configuration now. So I've got that configured in WordPad here. You'll see that you'll do this a lot in the real world as well. Where you have common configurations that you're going to use on multiple routers, it's easiest to write them down in a text editor, and then you can copy and paste from there. Also in the real world, you'll usually have templates that you'll use for common configuration for your routers and switches too. And whenever you provision a new router or switch, all you'll have to do is take that template, change the IP addresses in there, and then any other specific settings, and then you can copy and paste that into the router or switch. It makes it a lot easier that way. It also stops you from making errors as well. So that's what I'm going to do here. I've got my basic RIP configuration typed out in a text editor. So I've got router RIP to enable the protocol. I'm going to run version 2 rather than version 1. I'm not going to do automatic summary at the classful boundary, and I'm going to enable it on all my interfaces that are in the 10 network. Again, don't worry too much about the config for now. We'll cover this in more detail later. So I'm going to copy that from my text editor and then go to the lab, and I'm going to paste this in on each of the routers. So I'll do it on R1. I'll also do it on R2. Oops, R2 on R3. I should have put config T in the first line of the text editor, and that would have made it a little bit easier for me, but that's okay. I can just type that in each time. So just exactly the same config on all of my routers. Now I'll go to one of the routers that was in the middle. That was R3. and I'm going to do a debug on here. So debugs are similar to show commands, but where a show command gives you a point in time snapshot
All the
information,
likes. Hit the
debug
like,
information
smash
gets
that
updated
fucking
in
like
real
button.
time. You'll see what I mean now. So just like show commands, debug commands get entered at the enable prompt, and I'm going to debug IP rip. And I should start seeing the updates being sent and received on here. So there you go, I saw a RIP update being received from 10.1.0.2. Let's just check the topology. So I'm on R3 right now, and 10.1.0.2, that was an update coming in from R2. I'm also going to see updates coming in from R4 on 10.1.1.1 as well. So R3, because I enabled routing protocol on all my routers, they will form adjacencies, which each of their directly connected neighbors, and they will start sending updates to each other. Not just about their own directly connected routes, but about all the networks they've learned from the other routers as well. So R3 should receive information about the 10.0.0.0/24, the 10.0.1.1/24, and the 10.0.2.1/24 network from R2. Also the 10.0.3.0/24 as well. It's also going to be sending out updates to R2 and to R4 as well. So if I jump back onto the command line, you'll see that yes, it is sending and receiving updates. So if I scroll back a bit, you'll see that it's been receiving updates from 10.1.0.2, which was R2, and it's also receiving updates from 10.1.1.1, which is R4. It's also sending updates to those routers as well. So it's getting this information. If I now do a show IP route, you'll see that the routing table is updated. Actually, let me just turn the debugging off as well to save it updating anymore. The command to turn off all debugging is undebug all. After you've entered this, you might still see a few debug outputs coming in, but it will turn it off. So let's just scroll down a bit and do a show IP route, and you'll see that my routing table has now been updated. So you see the codes up at the top here tells you the way that that particular network was learned about, whether it's directly connected, a local route, whether it's...
I'm an idiot. Just FYI. I'm gonna fix what I did wrong. I don't know why I was creating different networks for each interface for some reason. I don't know why I was thinking that. But we're gonna fix it. There's no reason why I was doing that. So they're still down. Good, good. Glad I thought about it. So let me go back to each one of these and delete this shit. Boom. I don't know what I was thinking, but glad I caught it. So I'm gonna do this. Where's this? Perfect. Perfect. Cool. Last but not least. All right. Perfect. All right. Back on track, boys and girls, with my madness. Ooga booga. All right. So he was running RIP. And
It's a manually configured static route, or if it was learned from a routing protocol, and which routing protocol it was learned from. So you see here the code R. If we look up a bit higher up here, and if I can find it, there R is RIP. So it learned the routes to the 10.0.0, the 10.0.1, the 10.0.2, and the 10.0.3 networks via RIP. Also on the left-hand side, 10.1.2 and 10.1.3. It is directly connected to all of the other networks. Well, with the example here, I didn't have any static routes set up beforehand, so the routers only knew about their directly connected interfaces. But when I enabled my routing protocol, they shared information with each other, and the routing tables are going to be updated in all the routers. If I jump onto R1 as well and do a show IP route here, you'll see it also knows about all of the networks in our topology.
a loop, how to enter. I have definitely broken ChatGPT. That's good. It's done. Back address. What did he run?
Which is R4. It's also sending updates on all my routers. They will form adjacencies, which each of their directly connected neighbors, and they will start sending updates to each other. Not just about their own directly connected routes, but about all the networks they've learned from the other routers as well. So R3 should receive information about the 10.0.0/24, the 10.0.1.1/24, and the 10.0.2.1/24 network from R2. Also the 10.0.3.0/24 as well. It's also going to be sending out updates to R2 and to R4 as well. So if I jump back onto the command line, you'll see that yes, it is sending and receiving updates. So if I scroll back a bit, you'll see that it's been receiving updates from 10.1.0.2, which was our 1.0.1 get entered at the enable. Now I'll go to and then go to the lab, and I'm going to paste this in on each of the routers. So I'll do it on configured in WordPad here. You'll see that you'll do this a lot in the real world as well. Where you have common configurations that you're going to use on multiple routers, it's easiest to write them down in a text editor, and then you can copy and paste from there. Also in the real world, you'll usually have templates that you'll use for common configuration for your routers and switches too. And whenever you provision a new router or switch, all you'll have to do is take that template, change the IP addresses in there, and then any other specific settings, and then you can copy and paste that into the router or switch. It makes it a lot easier that way. It also stops you from making errors as well. So that's what I'm going to do here. I've got my basic RIP configuration typed out in a text editor. So I've got router RIP to enable the protocol. I'm going to run version 2 rather than version 1. I'm not going to do automatic summary at the classful boundary, and I'm going to enable it on all my interfaces that are in the 10 network. Again, don't worry too much about the config for now. We'll cover this in more detail later. So I'm going to copy that from my text editor and then go to the lab, and I'm going to paste this in on each of the routers. So I'll do it on R1. I'll also do it on R2. Oops, there's R2 on R3. I should have put config T in the first line of the text editor, and that would have made it a little bit easier for me, but that's okay. I can just type that in each time. So just exactly the same config on all of my routers. Now I'll go to one of the routers that was in the middle. That was R3. And I'm going to do a debug on here. So debugs are similar to show commands, but where a show command gives you a point-in-time snapshot information, debug information gets updated in real time. You'll see what I mean now. So just like show commands, debug commands get entered at the enable prompt, and I'm going to debug IP RIP. And I should start seeing the updates being sent and received on here. So there you go, I saw a RIP update being received from 10.1.0.2. Let's just check the topology. So I'm on R3 right now, and 10.1.0.2, that was an update coming in from R2. I'm also going to see updates coming in from R4 on 10.1.1.1 as well. So R3, because I enabled routing protocol on all my routers, they will form adjacencies, which each of their directly connected neighbors, and they will start sending updates to each other. Not just about their own directly connected routes, but about all the networks they've learned from the other routers as well. So R3 should receive information about the 10.0.0/24, the 10.0.1.1/24, and the 10.0.2.1/24 network from R2. Also the 10.0.3.0/24 as well. It's also going to be sending out updates to R2 and to R4 as well. So if I jump back onto the command line, you'll see that yes, it is sending and receiving updates. So if I scroll back a bit, you'll see that it's been receiving updates from 10.1.0.2, which gives you a point-in-time snap. I'll go to one of the routers that was in the middle. That was editor, and then go to the lab, and I'm going to paste this in on each of the routers. So I'll do it on R1, I'll also do it on R2, oops, R2.
Alright, we'll do that. So we'll start off with RIP as our first protocol. What time is it? It's getting late. This will at least get us started with doing that. So what I want to do first is, actually, let me put this all on before I start putting up. Let me bring all the interfaces up, because that's gonna take a hot minute to do interface anyway. So let's do interface 0, 0. I should have turned them on as I was going along, but I'll say it wasn't. That is true, isn't it? I was right. I was right. So not a deal. Right, I'll fix that. Practice makes perfect, right? Just one. What would be a subnet mask that has no more addresses? I'll look it up. Good. Alright, now that we're back from our... Oh, I didn't even turn on... Alright, everything's up. 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 Last but not least. And when we get to Ansible, at least let's get to Ansible. We'll be able to get this all automatically configured in seconds. Just have to write the script. All right. Let's fix it out there. Let's do some show commands. So let's show CDP neighbors details. And what are we seeing here? R1. Total. I can see that. Let's go over to R3. There might be multiple on this. Let's actually just exit out of here. Oh. Yeah, so we do. That's cool. So we got R4. It's showing. And it's showing R2. And it's 1. We'll have 2 again, 2. And oh, they got 3. That's right. That's right, because I got 1, 2, 3 neighbors. So that's why they're showing 3 inside of their CDP. Like remember that Cisco device, Cisco Discovery Protocol. And we're already learning some information about some of our neighbors here. Got R3, got R5, MAC addresses, IP addresses, R2, MAC address, IP addresses. Cool. Cool. Alright. Now that that's all set up, I guess when we get down to R5, take a look at some of the stuff.
All of the different routing protocols. So I'm going to use RIP, the routing information protocol, for this demo, and I'll show you the configuration now. So I've got that configured in WordPad here. You'll see that you'll do this a lot in the...
So we're going to configure RIP version 2. No auto summary. I'm guessing the auto summary command that is it probably populates on it. So we probably the network will be with 192.168 network. .0.0. That way it encompasses all of the networks. Let's get that configured on our routers, like he says, on our routers. So let's just write down those. So in configuration, terminal mode, we got router. Bring this back so you guys can see. So in global configuration mode, we have router RIP. Then we have version 2. We're going to identify the version we want to use. And then we're going to be using the no auto, no summary. And then we're going to be using for the network network 192.168.0.0. That way it encompasses it, all of that. Now this is static, you know, this is kind of static leaves, but this is good for now. We're gonna get into OSPF and all that soon. So those are the couple of commands that we're gonna use to get into this. So I'm gonna copy, paste this. No auto summary, so that's the better way. So let me fix that. Okay. And this last one, we want to look at some of the debugging messages here he was doing. So debug. And then we're gonna do the all right, so we'll see if we get some of these RIP messages here. I'm not too sure.
So there you go, I saw a RIP update being received from 10.1.0.2. Let's just check the topology. So I'm on R3 right now, and 10.1.0.2, that was an update coming in from R2. I'm also going to see updates coming in from R4 on 10.1.1.1.
Okay. I'm gonna be done in a minute. Okay, router bit version 2. Time. Now let's do this. Excuse me. There we go. Now we're starting to get some back entry here. Do a show. So what if I do this then? Yep. We're getting all the updates now. Mm-hmm. We'll do that real quick and turn debugging off. All right. Let's take a look at what we got going on. Get that squared away. All right, so. Cool. So let's come over here. Hmm. I have broken ChatGPT. Suck at rip. I'm ripping it up on rip. I have broken rip. It's gotta be my configuration. It's gotta be fucked up somewhere. And is the auto summary thing that's screwing me here?
For coffee, 10.
All right, let me I go wrong. IP routing is MC aware. Sending out. Routing protocol is RIP. Yeah, that's what I wanted.
Yeah, 7 scoops. Yep.
It's version 2. Misteria. Oh, gotta go bathroom. Be right back. I'm gonna smoke a quick cigarette, guys. I'll be right back. Alright, let's get back to it. Let's figure out why rip is not ripping. Which is the only time to see if anything's updated. Oh, IP route, dumbass. That's fine. Oh, it's interface. Yeah, let's do that. Begin with interface. This is why one config R2 R3 and so on. changes. Is that instance. Do. The network command root specification. Just choose this response, please. Oh, you okay? Okay. We'll be participating. All interfaces included. See if I can remake the connection real quick. Oh. Did it fix itself? It's still buffering. Kind of fix itself. Yeah. Okay. Alright. I should be done soon too. FYI. Wasn't that it was too, but still too. much back to basics again. Passive, some updates. Passive interfaces. Because of that too. I think where I'm messed up at is this was me is this. This is a network. This is me